a little bit more about laws of logarithms, and this room is horrible. I hate this room. It's funny to look into. It's just weird. I'm used to that one so much. So let's start with something easy. Let's start with this one. So this is the last couple sections. Quick little rundown. There are several types of solving equations. This is just one of them. And I'm pulling this right from the final, so you can see what kind of questions I'm going to throw at you for this section. So the purpose here is to solve for x, obviously. And the only way to do it is to create a one-to-one situation. And that one-to-one situation is to get the bases of these two things to be exactly the same. So what base can you make 27 and 9 to be exactly the same? Think exponents. 27 can be rewritten as what? 3 to the third power. So you change 27 into 3 to the third power. You leave it raised to the 4 minus 2x. What about 9? 3 seconds, 3 squared. And it's going to be raised to the 4x plus 4. Okay. Now, when you get to this part, it's going to be the base is now 3 for both of them. And you have this exponent to an exponent on both sides. So what can you do with an exponent to an exponent? Ah, come on, multiply. Power to a power, you multiply. Base times base, you add. So you're going to multiply this out, and it's going to distribute. So you're going to get 3 raised to the 12 minus 6x is equal to, it's going to distribute through the power.
3.
And here it's going to be 8x plus 8. So you get 3 raised to the 8x plus 8. Now, I talked about this next part earlier. If they have the exact same base, they're technically the same function. It's some base raised to a power is equal to some base raised to a power. That's the same thing as f of b is equal to f of a. If f is a one-to-one function, which exponential functions are, then what must be true about b and a? They're exactly the same. So b has to equal to a. So here, you think of this as b, and you think of this as a. So they must be equal to each other. So this is called the one-to-one property. There's no algebra going on. You're just recognizing that the powers have to be exactly the same. And then you get this nice little linear equation. How do you solve? Well, yeah, that's the last step.
Combine like that?
No like terms on either side.
So add x.
Get the x's on one side, get the junk on the other. So add 6x across, you get, what, 14x? And then subtract the 8, and you get 4. And x equals 2/7 after you divide by 14. So that's just a one-to-one property. It's kind of a neat idea. I don't think I wrote that one down, but I can make up one. It also works with logs. If you have a log function on both sides, you can use the one-to-one property to solve it. And the one-to-one property says, well, these are both log base 3. So what must be true about the n sides? They have to be equal to each other. So you get x squared minus 6 is equal to 5x. How do you solve that equation?
Square root.
No, you do not square root it. What kind of equation is it? Kind of equation?
No.
No? This one over here was linear. Quadratic. So how do you solve a quadratic equation? What's your main step? Get it equal to 0. So you get x squared minus 5x minus 6 is equal to 0.
Oh.
Oh, remember these things? How do you solve this equation?
You can choose any kind of form. You can get
Oh, you
Well,
can
you
use the
can complete-
quadratic formula, but that takes too long.
factor.
By factoring. Factors of 6 and subtract up to 5.
2, 3. No, 1 and 6.
1 and 6. So this factors into x minus 6 and x plus 1. So far, so good. And then when you set them both equal to 0, you're going to get x equals 6 and x equals negative 1. All right. Now here's the trick. Remember, it was Wednesday. I was talking about the domain of the logarithm function. The number on the inside can't be negative. So does 6 cause any problems? Well, 6 squared is 36. 36 minus 6 is 30. 5 times 6 is 30. That's perfectly fine. What about negative 1 now?
It's going to be negative.
It's going to force this one to be negative, and that one too. So we can't use that as a solution because it causes a negative inside the logarithm, which you can't have. So the only answer here is x equals 6. Aren't these easy so far? Oh, it's horrible.
But my hair hurt.
Already? I haven't even done the hard stuff yet. Short boards. How about, let me steal one from here. Let's warm up with these. We did these last class, but I want to make sure you know what you're doing. Log 2x plus 5 is equal to 3. I'm going to solve for x. Just 3 left. All right. How do you think we're going to solve for x? Can you do it the way it looks?
At log of T3. No, wait.
I know what you're saying. You're trying to say it right.
Wait.
What's the important thing? Whenever you're dealing with exponentials or logs, there's only one important thing.
The base.
What is the base?
10.
10. So you write down 10. What's the exponent? 3. And it has to equal 2x plus 5. Can you solve for x now? 10 cubed is 1,000. And it's going to equal 2x plus 5. How do you solve for x?
Subtract 1.
Subtract the 5, this becomes 995 is equal to 2x. And divide by 2 and you get x equals 995 divided by 2. Perfectly fine answer. And it won't cause any trouble because when you plug it in, it gives you positive numbers. Isn't that neat? I love this stuff, it's so easy. How about this one? ln of 4x minus 3 equal to 2. What's the important part?
The base.
What's the base? E raised to the second is equal to 4x minus 3. Solve for x. Add 3 across. Don't find out what e squared is. Just leave it as e squared. It's perfectly fine. And it's going to equal 4x. How do you finish it? Divide by 4. And you get x equals e to the second plus 3 all divided by 4.
Oh, that's easy.
Yeah, that's what I'm saying. Usually this chapter is very simplistic.
It's like when you were first doing it.
You just got to get used to the rules and how to convert logs into exponents, exponents into logs, rules of logarithms. That's the next one. How about this one? Log base 3 x minus 4 plus log base 3 x plus 2, and it's equal to 3. Now, why is this one different than the other two?
You had 2 times.
Well, the other two had a single log and a number on the other side. This one has 2 logs and a number on the other side. This method only works if it's a single log. So is there a way of writing that as a single log? Contracted. Constricted. Sounds like a snake. Constrictor. Contract. So if you contract these, how do you rewrite it? Log base 3 of what? Just by itself.
Huh?
When you see a plus between
Oh.
two logarithms, what's that mean?
They must be
You multiply. And what am I multiplying? No cross multiplying. Multiply. So what am I multiplying?
X minus 4
X minus 4 and
plus X plus 2.
X plus 2. So it would be X minus 4 times X plus 2. And this whole thing is equal to 3. The sum of the logs becomes a product. The log of a product becomes a sum. All right. Now I have a single log, just like these other two. What do?
So
3,
The base is 3. The exponent is 3. And it's equal to,
X minus 4, X plus 2.
and if you multiply that out, you get x squared minus 2x minus 8.
Well, see, you can still do the cross multiply to begin with.
There, that's not cross multiplication.
I mean, that, oh, you know what I meant.
What are you doing?
tell me who
This is what happens when you come late. You didn't tell them any answers, did you? All right, how do I solve?
3 squared. I mean 3 cubed is 27.
So this is 27 equals x squared minus 2x minus 8. Then what?
And
Come on,
You always say combine. What kind of equation is it?
subtract
yeah,
27.
factor.
Because it's a quadratic, you want to get it equal to 0. So you go 0 equals x squared minus 2x minus 35. I think.
Mhm.
Now what?
Factor.
Factors of 35 and subtract up to 2.
5 and 7.
5 and 7, so you get x minus 5, no, it's x plus 5, and x minus 7. And they're both equal to 0, so you're going to get x equals negative 5, and x equals positive 7. Oh, these quadratics keep showing up all over the place. No wonder I've put so much emphasis on them. Can it be both of them?
Mhm.
Why not?
Because I'm calling it negative.
Yeah, this negative 5, if you plug it into either of the original terms, is going to cause a negative in both of them. You can't take the log of the negative, so that one goes away. Erroneous solution. So the only answer is x equals 7. See, these really aren't that bad. You just have to remember a few little basic things. All right, so that leads us to, well, I might as well do that one. This is like a review question. Well, all of these turn into review questions. How about 4e to the 2x plus 18e to the x minus 36 is equal to 0? Number 1, what does it look like? It looks like a quadratic. Do you remember the method? Yeah, that u equal thing.
Mm.
So you say u equals?
18. No. Oh no.
U squared.
E to the... Do I look at the first one or do I look at the middle one?
Middle
The
one.
middle one. And you just let it equal the variable part, which is e to the x. So u equals e to the x. Then what do I do?
U
Square both of them. This becomes u squared equals...
E squared.
E2
Well, what's e to the x squared? E to the 2x. It should be the first term. So e to the 2x. So this turns into 4u squared plus 18u minus 36, and it's equal to 0. What do you do?
Go, plug it into the
Quadratic formula. Please don't do that. Before you try.
factor.
Factor. Now, what's common between all of these? Because GCF should be your first hint. 4 common to all of them? 4 goes in 18?
2.
2. So you either A, factor out of 2, or B, divide everybody by 2. Because there's a 0 on the other side, so it'll just go away. I'm going to divide.
Is that the same thing?
It comes out to be the same thing. So this becomes, what, 2u squared plus 9u minus 18 is equal to 0. Now, you can use the quadratic formula if you so desire, but I highly suggest you try factoring first. 2 times 18?
36.
36. Are there factors of 36 that subtract up to 9?
I don't know. It should be.
There should be.
4.
4 and...
Hold it, what is?
Factors of 36 that subtract up to 9.
Oh,
11.
12 and 3.
12 and 3.
Oh, yeah.
So, 2u squared plus 12u minus 3u minus 18 is equal to 0. Everybody forgets the easy ones, 12 and 3. You're all like 9 and 4, 6 and 6. All right, GCF of the first two?
2.
2u, left behind is u plus 6. The GCF of the second two?
-3.
Negative 3, left behind is u plus 6. Still equal to 0, so our factors are u plus 6 and 2u minus 3. And it's equal to 0. Great. Problem is, I'm not really looking for u. I'm looking for what u is equal to, which happens to be e to the x. So when I solve this, I get u equals negative 6, but that's e to the x is equal to negative 6. It's going to give you u equals negative 6, but u is equal to
Okay, I'm gonna have to write all of it.
E to the x. Okay. This one is 3 halves, so you're going to get e to the x is equal to 3 halves. Okay.
What?
Where? If you solve this one, 2u minus 3 is equal to 0, you get 3 halves, but u is equal to e to the x, so I'm just doing a substitution. In other words, I'm running out of room and I want to get to the answer. Problem, I need to solve for x, so how do I get rid of the e? There's 2 ways of doing it.
You can't read negative 6 now, can it?
Well, that's actually a good question. Can e to the x ever equal negative 6? No, because anything you raise the power to, it's going to be e raised to a power. And since e is positive, whatever you raise it to is always going to be positive. E's positive automatically. And exponents can be positive or negative. But it'll bring you down, but it'll never cross 0. Remember that graph? It kind of hugged the x-axis but never went below it. Another way of solving this, though, is to change it into a logarithm. How do you change it into a logarithm? What's the base? It's going to be ln because the base is e. So you get ln of negative 6 is equal to x. There's a problem with that one right there. Well, that negative. You can't have a negative inside a logarithm. So that's another reason that you can't use that one. All right, doing the same thing over here, this becomes ln of 3 halves is equal to, and that's your answer. Isn't that neat? I love problems like that.
You see how I can get it like this? Like, you get
Notice
my
how
head.
close you are now, too? You should have been sitting there all semester. No, you wanted to be the social butterfly in the corner. And this is recording for the future people that take 161, and they're going to hear me saying that to you. No, that's all right. Sorry, people. All right. What else? Ooh, this one. This is also a test question. This actually goes back to the laws of logs. So I'll tell you that the log some base of 3 is equal to a specific number. The log base b of 5 is also some kind of specific number. And the log base b of 2 is also a specific answer. Do you care? No. These are just things that are given to you and you just accept them as set in stone. And then I'm going to ask you to evaluate this. Oh, that's a 4. 4th root of 27 over 16. So the only thing I'm given is log of 3, log of 5, log of 2, and its respective answers. And I need to evaluate this thing. So what do you think I'm going to have to do with all these numbers that are in here, the 25, the 27, and the 16? Well, in what way? Because I don't know anything about 25. But I do know something about 25 in terms of one of these original numbers. What's another way of writing 25? 5 squared. What's another way of writing 27?
3 cubed.
3 cubed. What's another way of writing 16? 2 to the... I have to use one of these numbers. So it has to be 2 to the 4th power. So I can rewrite this as log base b of 5 squared, the 4th root of 3 cubed over 2 to the 4th. That might help. All right. I don't like this 4th root of 3 cubed. What's another way of writing that? 4th root of 3 cubed. What can you do with a 4th root and change it to an exponent? You don't remember? How do you evaluate 8 raised to the 2/3 power? What's the 3 represent? It's a cube root because it's in the bottom. So if I have a 4th root, I can rewrite this whole thing as 3 to the
3/4.
3/4, because the 4 has to go in the bottom. So this is equal to log of 5 squared times 3 to the 3/4 power over 2 to the 4th. Log base b. Log base b. All right, now what can I do with it?
Simplify.
How? There's 2 things you can do with logarithms. Earlier we contracted them. We can expand it. So how does this expand? Well, it would be log base b of what? Of 5. Where's the 2 go? By the laws of logarithms, exponents go where? In front. So this becomes 2 log base b of 5. All right, the other thing on the top is what? That 3. So do I put a plus or a minus here? Plus, because it's in the top.
3/4.
The 3/4 goes out front. Log of 3. Let me put parentheses here. All right, what's the last piece? That 2.
Over the
Subtract.
Subtract.
4.
4. Log base b of 2.
Okay, so every time you have a bar, you subtract.
Anything that's in the bottom is negative, automatically. Anything in the top is positive, exponents go out front. That's all you need to remember. Now, we can do substitution. We know what log base b of 5 is equal to. It's this 0.8271. And log base 3 is this 0.5646, and hopefully you all have your calculators, because now you need to type in 2 times 0.8271 plus 3/4 of 0.3562 minus 4 times, oh, wrong one there. This one's 0.5646 minus 4 times 0.3562. And it gives you an answer. Why? Oh, you're lazy. It's Friday. Oh,
I got 0.74285.
confirmation?
85.
8.5. Confirmation?
Hold on. Let me redo it.
I don't trust first person's calculations until someone else gets the same answer. Too many ways of typing things in badly.
Oh, I got it wrong. I put point.
And this is why I don't trust first calculations. Kill that one.
Decimal 65.
Decimal 6.5.
285.
2.85.
Yeah, I got that.
2 people got that
Let
one.
me
I'm
recheck
trusting
it.
it now. 65285. And probably on the test, I think it's rounded to 4 decimal places, so it'd be 6529. I think. What's it say on here?
That's correct.
No, it just says write the answer, so just write the answer. Be done with it.
Hopefully you don't have no decimals on the test. You like this.
Just like that, yeah. I mean, I took that question right from the exam.
Oh.
I
The
printed off
same numbers
another.
and all that?
What's that? No, they change automatically. But the pattern stays the same. Nothing changes about that.
So it's still gonna be like the same
Same idea.
questions.
You
and
see
just
this junk
different
here.
numbers.
Yeah, you see this junk here, and you look for powers that come up with these three numbers that are related to the original three. And then you bring powers out front, positives for the top stuff, negatives for the bottom stuff. Substitute the numbers in and do it. It's a simple problem. It's just if you don't know the laws of logarithms, you'll never solve it. All right, so that leaves us with the last little bit. Applications. And I'm not going to go crazy on you. And generally, the applications aren't horrible. They're actually kind of easy. And there's two types of applications. There's growth application and decay application. Growth application comes from looking at an exponential function that has a positive exponent and a base bigger than 1. And you get the general picture of an exponential. Now the growth is occurring from the y-intercept on, so we're really only talking about this part of the graph. And we've looked at one formula that deals with growth so far. You remember that formula? So some of the applications might have to deal with this, but more than likely not, because this one is just dealing with money. And what happens here is you only earn interest at the end of every single month. So between 1 month and the next month, nothing is happening until you get to that month, and then your money jumps up. So it's not a continuous function. It's a very choppy, it's actually a piecewise function if you look at it right, according to T. Now, there was another little formula that looks similar to some of this up here, and it was that E is equal to the limit as x goes off to infinity of 1 plus 1 over x raised to the x.
You never have one.
Well, that's not a formula you need to memorize. It's just really a definition of what E is equal to. It's just a definition. And there's a lot of similarities between these two setups. This one has 1 plus a fraction raised to some power. This is 1 plus a fraction raised to some power. Now, I could show you the algebra, or do you want me to just give you the formula? This is the only time I will let you choose.
Just give us one.
Oh, you're no fun. So what happens is if we kind of mix and match these two ideas, is we get this new idea, which is continuous growth. And it can be really quickly switched into decay. It really depends on the exponent. So if I mix these two ideas together and I do a little fancy algebra, I can prove to you that we can rewrite A. N would go off to infinity, so we're talking about infinite number of compounding. Now, remember I changed it the other day from 10 to 100 to 1,000, and the money approached a certain value. Well, that formula would be what I call PERT. I like PERT because it's a word, and it's easier to memorize than the formula in the book. The book uses this. It is the exact same formula. It's the exact same formula. It's just, instead of talking about P, you talk about A sub 0. Now, you've seen sub zeros before. V sub 0, S sub 0. One was initial velocity. The other one was initial distance off the ground. A sub 0 is just initial population. So you either use P for population or A sub 0 for population. It doesn't matter. If you like PERT, great. If you like the book one, great. I could care less.
What's the K?
K is the same thing as R. It's just different choices of letters, that's all. I mean, algebra is just replacing numbers with letters. Does it matter which letter? No. Some formulas don't use A, they use F for final amount. Instead of talking about just plain old amount, they talk about it as final
See,
amount.
that would be confusing because I think I'll be looking for the wrong
But the setup is exactly the same. It really doesn't matter. All right, so what happens here is if R is greater than 0, or for that matter, K is greater than 0, positive numbers, we are talking about growth. If we have money in the bank account and its interest rate is a positive, it better be positive. Imagine if you had an interest rate that was negative. And you save money, then you expect your money to grow. And if R and or K is negative, depending which formula you want to use, This is going to be decay. What types of things decay continuously?
Bodies.
What is it? Bodies, yeah, bodies do decay. And they do kind of follow the decay thing, but we're talking about a substance decaying, actually. Nobody? Have you ever heard of carbon-14 dating? Don't you take science classes?
I heard of it in biology.
Yeah, biology, carbon-14. How's it work? Well, every living body on the planet has a specific amount of carbon-14 in you, and it's a radioactive isotope. Yes, you are all radioactive to a point. So trees have it, grass has it, leaves have it, we have it, animals have it. When you die, you stop absorbing carbon-14 because now you're not bringing food into your system. Trees aren't bringing water and nutrients from the soil. They're dead. So that carbon-14 starts to decay and it's a very constant decay thing. So they can age things. They can find out how old things are, like a cave drawing that's done in charcoal. Charcoal comes from dead trees. You know, you burn it and you draw with it. Oh my gosh, you guys are just like, oh. But it comes from dead trees. So they drew with charcoal, and you can date the charcoal by scraping it off and finding out how much carbon-14 is in it. And it'll tell you how old that cave drawing is, approximately, give or take a few things. So that would be one application of a decay.
Have you ever taught science?
Nope, but I know enough about it. Sad, isn't it? I know too much as it is. Other things that decay. Nuclear power plants. Does their fuel last forever? No. What do they do with it when they're done with it?
Dump it.
Where? You can't just throw it in the garbage landfill because it's still, well, kind of radioactive. You've heard of this. You know, you have this radioactive waste and you have nothing to do with it because it's going to be radioactive for a very long time because it is decaying. But most of it decays over thousands and thousands of years. So we have this nuclear waste, and we're like, where should we put this? So they drill holes into mountains and put it in the mountains. But they'll have to be secure for thousands of years. Otherwise, you get contamination to the water table and all that. That's why it's a huge problem.
Well, they drill holes in the mountain.
Yeah, they drill a hole in the mountain, create a cave, they throw the nuclear waste in there. But they're in these secure containers, and the room is secure. But is it always going to be secure? Thousands of years. What could happen? Earthquakes, floods. I mean, we don't know. And then all this nuclear waste is going to leak out. So if you live next door to a nuclear power waste dump, you're going to be glowing, or your descendants will be glowing. So one possible application is this. A jar starts with 50 fruit flies.
Talk about fruit flies, biology.
Yep, because they're quick growing and you play around with genetics. Actually, that's the end of the sentence. After 5 hours, there are 75 flies. Find growth constant. That'll be the first part. Find the growth constant. Now, since fruit flies are growing continuously, we can't use the compound interest formula. We have to use the PERT one or the A sub 0 one. Which one do you want me to use? They're the same. It's just PERT. I like PERT just because it's easier to think about. So A equals PERT. Just make sure the RT is an exponent. Now, in this case, the growth constant is R. In the other one, it's just K. It's the same thing. It's just what position is it in. So we're going to try to solve for R. So do I know what A is equal to? A is the final amount after a period of time, by the way. So this is 75. P is? P is usually the population, beginning. That's why I like A sub 0 because it's initial population. But this is 50. E to the, do I know R?
5.
No, that's what I'm looking for. Do I know T?
5.
And it's 5 hours, so whatever measurement we use, it has to be hours. Let me just peek it up. 2 suckers left. Okay, how do I solve for R? What would I do first? What's the only thing that I can move algebraically? The 50. It's the only thing that moves. You can't touch the 5, you can't touch the r because they're exponents. The 75 is useless because it's not even on the same side as the r. So the only number that you can touch is the 50. And the only thing you can do to it is divide it. So what's 75 divided by 50?
3. 3.
3.
Oh no.
It's not 3.
Oh no, it ain't 3. 3.
1.5?
She wrote. Oh, you want a decimal.
Oh, you said 3 halves?
She said 3 times.
3 halves? Yeah, 1.5 or 3 halves. We can go with decimals this time though. So 1.5. The other side is e to the 5r. Now you have two choices. You can either A, rewrite this as a logarithm, or B, use the inverse property of logarithms. Both of them come up with the same answer.
Which one easier?
Which one's easier? Actually, neither. They're about the same.
Yeah.
Rewrite it. So if I rewrite it, it becomes
And
ln, because it's base e, of 1.5, the other side, is equal to 5r. How do you solve for r? Divided by 5. So you get r is equal to ln of 1.5 divided by 5. Type that in your calculator and get a nice little decimal answer. It can't be negative. It will not be negative because ln of 1.5 is positive.
Is it 0.08?
0.084?
No, 1.
1.081. So this is your growth constant. Basically, it's saying your population is growing at a rate of about 8% per hour. If you want to think of it that way. All right, there's a second part to the question that could come up. Once you find the growth rate, how long until you have 200 fruit flies, FFs. 200 fruit flies. So what changes?
The numbers.
Well, a couple of the numbers. You're still going to use this formula. So bring this over. The A is now 200. The P is
50.
still 50. That doesn't change. E to the,
R.
but I know R now.
Oh,
0.081. The thing that I don't know is
T.
T. So T becomes the variable. So if you write RT, you have to recognize you're dealing with two variables and you must know one or the other. I don't know T. Over here I knew T to get R, but over here I've increased my population. It's going to take longer, but I don't know how long. So how do I solve for T?
Divide by 50.
It sounds exactly the same as that one. Divide both sides by 50. 4. So that becomes 4 equals e to the 0.081t. Use the ln feature. So this becomes ln of 4 is equal to 0.081 times t. How do you solve for t? You take ln of 4 and divide by 0.081. And you get an approximate time. It better be longer than 5 hours. 17? So it's approximately 17 what? No, not decimal. Measurement system. What do I measure this in? Feet? Miles? Days? Hours. Because time was measured in hours at the very beginning.
how you get 17?
I don't know. They typed it in their calculator. ln of 4, close your parentheses, because otherwise you're going to be doing ln of 4 divided by point, and that makes a mess. You get a negative. No, it'll be a positive number. So that's an application of population growth. Are you whining? You're whining. Let's talk about decay. used to remember this number. Oh, I can look it up. Hold on. Let's look it up.
Oh my God,
Half-lives, yeah.
where her problems on this test.
Half-life carbon 14. 5,730. 5,730 of 5,730 years. Okay. Now, what the heck does a half-life mean? Well, if you start off with 200 grams of carbon 14, all right, after 5,730 years, you would expect about half of it. So what's half of 200? 100. So after 5,730 years, 200 grams of carbon 14 you started with will now only have 100 grams. The rest of it turns into carbon 12, I think, which is normal carbon. After another 5,700 years, you'll end up with 50. After another 5,730 years, you end up with, and so forth and so on. You'll never ever run out of it. There'll always be a little bit of carbon 14 in everything. It's just that it will get really, really small. It's still a long time. So this is my problem. I have this carbon 14 has a half-life of this. I need to find the decay rate, or decay constant, which is the same thing as the growth rate. It's just, in this case, instead of being positive, it's going to be negative because it's decaying, it's coming down. So we set up our formula. We say, well, A equals P per, E-R-T, a pert. It's a shampoo, yeah. That's how I remembered it in school. Because I used to use pert shampoo when I had hair. But, yeah, I used to use, conditioner and shampoo all in one. But I guess it did this to me, so don't use pert. It'll make you go bald. All right, now, here's the question. Do I know the total amount? Kinda. Do I know the beginning amount? No. But I know there's a relationship between the beginning amount and the final amount. What relationship do they have after 5,730 years? Half. So if I start off with P, how much do I end up with? Half of P. So over here you go, half of P is equal to P-E-R times the time, which is 5,730 years. Gotta love Google. Google's awesome. You can find anything out on Google. All right. How do I solve for R? What do I get rid of first? The P. No, I can't get rid of the P-E. I have to get rid of the P. E's locked in because there's this exponent, so the only loose one is P, and I care less about the other side. So you're going to divide both sides by P. The nice thing here is what happens to all my P's. So this one is irrelevant to how much you started with. It just matters on you're ending up with half of it. So you get a half over here is equal to e to the 5,730 r. And then, well, yeah, you can change it to an ln. So it becomes ln of a half is equal to 5730 r. It would be ln of the other side is equal to what's on the top or inside, depending on how you want to look at it. How do you solve for r? Divide both sides by that 50 whatever, 5730. It's going to be negative. Don't let that frighten you. ln of a half is actually a negative number. No, it's not crazy. It's just the way things work. I can explain it real quick. Yeah. The ln graph looks like this. It's going to be negative. And this point right here is 1, 0. So if you go to the right of 1, 0, the graph is positive. If you go to the left of 1, 0, it's negative. So ln of a half has to be a negative value. Negative what?
1.2.
Times 10 to e to, that e negative 4 at the end means times 10 to the negative 4th. That means, no, that means you have to move this decimal 4 times that way. So this is actually negative 0.12312.
Why the calculators don't do it
That's
itself?
what I got.
That's what I
Big
got.
calculators
I got
change it
zeros.
into scientific
Yeah, I got
notation. Little
That's what
ones
I got.
don't.
Zeros.
Little ones don't.
That's why I was
Not until it
sitting
gets
on
a little bit worse. So you got to be careful. If it says e negative 4, you got to take that decimal and move it 4 times to the left. If it was positive 4, you'd move it
Well,
4
we
times
forget
to.
that you know what we talking about, right?
Well, now you know.
That's crazy. But mine came out just like
Yeah,
that.
yeah,
That's
because
why I got
yours has got a different threshold. Calculators have a threshold of scientific
This one
notation.
be the
It's a smarter calculator, yeah, it's supposed to be. All right, and then we can ask, how old
Oh,
You know.
is something that has 10% C14 left? In other words, it has 10% of what it should have in it to begin with, of a modern plant or a modern person or modern charcoal or whatever. All right, so the setup is exactly the same. What do you think is going to happen to the peas?
It might go away again.
They're irrelevant to begin with because I don't know how much we started with. I just know how much we really ended up with. So when you say 10%, what's going to happen to, I mean, you start with p, what happens to the p on the other side? How do you find 10% of p?
multiply.
By 0.1. So this is set up over here is going to be 0.1p is equal to p e. I know what r is now. It's this negative 0.00012t. What happens to the p's? They go bye-bye. Then you get 0.1 is equal to e to the negative 0.00012t. How do you solve for t? You get ln of it. It's the same thing, so it's nothing different. It'll be ln of 0.1, and you're going to divide that by negative 0.00012, and that'll give you t. I have one more problem to do after that one. It's one we've kind of ignored.
Wait, no, we gotta make sure we get the right.
Oh, we're
answer,
getting there. We're getting there. I just
no,
have
the
one.
right answer. 'Cause you know
I'm warning you that there's one more problem
Okay.
that I want to do. So ln of 0.1, that's going to be a negative number. Divided by a negative number, you better get a positive number. How long? How old?
1988.
It is 19,188 years old. And that's how they carbon date things. It's really kind of a cool process.
see, I used to hate these problems because no instructor or no teacher showed me how to actually.
Do it?
Yeah.
Well, how would you be able to do it if you didn't know how to do it? That doesn't make any sense, does it?
Shouldn't that be
They
approximately?
didn't care back in high school.
Should it be what?
Approximately.
It's just approximately.
I can't say the name.
Yeah, approximately. It is approximately 19. It's not an exact science, but it's pretty close. All right, the last question is this. It goes back to the beginning. This is the equation that I set up to design logarithms. 2 to the x is equal to 40. We solved this thing. We solved it by logging both sides or converting it into a logarithm. Either one works perfectly fine, log base 2. And we got x is equal to log base 2 of 40. The problem is that I don't know what log base 2 of 40 is equal to. You can't type it into your calculator because your calculator only does base 10 and base e. It doesn't do log base 2. Fancy calculators do. You can change the base in the calculator. They're really fancy. That one even doesn't do it. At least I don't think it does. So the process, you can't do it that way. So we're going to go back to 2 to the x is equal to 40. And what we're going to do is instead of applying log base 2 to both sides, I'm going to use one that I know about. So I'm either going to use log or ln. Which one do you want to use? It really doesn't matter. I like ln because it only takes 2 letters. Log takes 3, but I'm just lazy, so I'm going to log. So if you log both sides, you get log of 2x is equal to log of 40. Ooh, didn't write it. There. I'm writing soft, I don't know why. What can I do to the left-hand side?
Pull the X out.
Pull the x out front. So this becomes x times log of 2 is equal to log of 40. How How do you solve for x? Divide both sides by?
2.
Not 2.
Log of 2.
Log of 2. It's another number. So the answer to x is log of 40 divided by log of 2. Make sure you put parentheses after the 40 and the 2. And you're going to just get an approximate answer. Approximate 5.3. And I can show you real quick that it is an approximate answer. What is 2 raised to the 5.3 equal to? Probably like 39.
Yeah, 139.
It's really, really close to 40, but it's not exact because there's a lot more decimals going on after that. So whenever you approximate an answer, it's not going to work perfectly, but it'll get you really, really close to the answer. There's a formula in here if you look at it the right way. If you have log base b of a, the formula says take the log of the top divided by the log of the little number. This is called the change of base formula. You don't have to memorize it. You can always just do this to get the answer, and it'll work every time. All right, well,